This video will continue the series I have on time value of money. In this video, we'll look at different compounding periods for an annuity. That'll lead us into effective annual interest rates. And then we'll look at techniques for solving problems for the number of periods N or solving for the interest rate. So now let's move on to pencil and paper to do the analysis. Let's look at different compounding periods for the present value of an annuity. We'll start off with an example. Let's do 4 periods. And the annuity is going to be paying $300 at the end of each of 4 years. And the interest rate, I/Y or just I, will be 6%. N is 4. We're going to have payment here of $300. Future value is 0. This is considered a payment. So, actually all of these numbers are in the future because we're starting right here. But these are all considered payments right here, this $300 payment. There is no future value given here. So future value is 0. And we're going to compute the present value of this annuity. What is it worth right at this point in time? Well, you put this into your calculator and you'll get $1,039.53. So how do you interpret that? Well, if you wanted to buy an annuity where you get $300 back for each of 4 years, starting 1 year from now, you would pay $1,039.53, provided that interest rates are 6%. So that's how you look at it. This is an investment. This is how much you'd pay for this investment that pays this amount. You'd pay, almost $1,040 for this. And you'd be getting a total of $1,200 worth of cash flow. Now the question becomes, in this problem then, what happens if you change the compounding period? Let's change the compounding period to be semi-annual. So when you have semi-annual compounding periods, you're now going to have twice as many periods. It's still 4 years, but this is the first 6 months, the second 6 months, and so this is still the first year. And then the third 6 months, fourth, and so on. So now it's semi-annual. And when we do that, we change N to now 8 periods, 8 semis. I'll just call it 8 semi-annuals. Okay, so we have 8 semi-annual periods. You have to take the interest rate and chop it in half because we just chopped every year in half. So the interest rate is now 3%. And we got to make one more adjustment. We're going to take this cash flow and chop it in half also. So we're going to get 150, let me cross this out. We'll get 150 here, 150 here. And now we're going to compute the new value. It's going to be different than this. And before we go any further, ask yourself, well, let me cross these things out. Is this annuity now with 8 semi-annual periods, will it be worth more than what we just calculated on an annual basis? You should ask yourself that. And if you think about it and you look at it really carefully, what has happened is you're getting cash flow a little faster in the semi-annual period. Because here you had to wait. When we got it annual and we had this $300, you had to wait an entire year to get that $300. Now we're getting 150 of it 6 months earlier than what we normally would. We're getting our cash flows 6 months earlier. So from that perspective, you can see that this is probably going to be worth a little bit more. And it will be. It turns out to be worth $1,052.95. And the reason for that is, like I just said, you're getting your cash flow just a little bit earlier. So if you can get your cash flow a little earlier, your present value is higher. The value of an asset that pays off sooner rather than later is more valuable, is another way to interpret it. I'll say it again. If you can get your money sooner rather than later, the investment that pays off sooner is worth more money, assuming all else is equal. And that's what you're seeing right here. Now, what we want to do is let's zero in on a particular year and look at how compounding works. And what I'm going to do is show you a year. So here we have 1 year. Then I'm going to say, look, we got this year. Now let's say it pays 8% right at this point. And if you just have annual interest, you're going to get 8% at the end of a year. So maybe you drop in $100 at this point, you'll get $108 right at this point. Okay. Now what happens if you turn this into semi-annual payments? So this is a half a year right here. So this is now it's 8% for a year, but now it's going to be 4% for this period, 4% for this period. And now we have 2 semi-annual periods. And we could even go further. We could say, well, why not break it up in the quarters? And so this 4% now becomes 2% here, 2% here, 2% here, and 2% here. And then you could break that up so that you get even smaller time periods where you get 1% for a half a quarter, and so on. So how does that work mathematically? Well, that's where the effective annual interest rate formula comes into play. It's computed as 1 plus the interest rate divided by M. And M is the number of compounding periods. When M is 1, it doesn't really do anything because you divide by 1. And that's when you have that 8%. And then if you do semi-annual compounding, you have 2 semi-annual periods. M will be 2. And if you go quarterly, M will be 4, and so forth. You go daily, M will be 365. And then we're going to take this to the M power and subtract 1. So 1 plus 0.08 in decimal, interest rate in decimal form for annual compounding to the 1 power. The 1s really don't do anything here. You subtract 1, and what are we going to get? We're going to get 0.08. In other words, the effective annual interest rate on annual compounding is the same thing. It's 8%. But if we do semi-annual, we're going to, let me change the color here. If we do semi-annual, M is going to be 2 right here. And this will be 2. And so what you're going to have is mathematically 1 plus 0.04 to the second power. So you're going 4% for a semi-annual period. There's 2 semi-annual periods. Don't forget to subtract 1. I often forget to subtract the 1. And what we'll get here is 0.0816. So you earn a little bit more from more compounding. You're going to get a little more than 8% in this time frame because you're getting cash flow, you're compounding sooner rather than later. Let me give you an example of a common problem we see in this course. The problem works like this. Which bank account would you prefer? A, 8% compounded annually, or B, 7% monthly, or C, 7.7% quarterly, or 7.5% daily. Which one would you rather have? Which is the best account for you? The way to do this is to compare the effective annual interest rates. Use this formula. Okay. Oops. Put that equal sign there. And let's do it here. So you don't have to do any math for an annual because you're going to get 8%. That's what I showed you a minute ago, because when you divide by 1, there's only one compounding period. It doesn't do anything mathematically. So 8% is 8% on an annual basis. Now, if you have monthly compounding, let's see what happens here. 1 plus 0.07 divided by 12 to the 12th power, because you're compounding over 12 months, that's going to result in 0.0723, 7.23%. Oh, so far the 8% is better than getting 7% compounded monthly. Now what about the 7.7%? 1 plus 0.077 divided by 4, because we're looking at quarterly, to the 4th power minus 1, and we get here 0.07925. So this is 7.925%. Ooh, that's better than B for sure, but still not as good as this choice A, this option A, where you get 8%. And then if we do it daily, ooh, do you think daily will bring us all the way up above 8% effectively? Well, let's do it. 1 plus 0.075 divided by 365 to the 365 power. And what do we get when we do this calculation? We get 0.0779, or 7.79%. So which account would you rather have? Make sure you guys can see that here. Which account would you rather have? Well, you'd rather have choice A here. 8% compounded just once annually is better than 7% compounded monthly. It's better than 7.7% compounded quarterly, and it's better than 7.5% compounded daily. So the effect of compounding, it's good, but it kind of wears out after a while, peters out after a while. So most of your compounding effects happen early on. In other words, when you go from annual to semi-annual, and then when you go to quarterly. But once you go past quarterly and monthly, the effects on driving up your interest rate is smaller, the change. And so you'll get a bigger interest rate, but it'll kind of slow down. So you get your most effects from semi-annual, quarterly, and monthly. And then if you go daily, you're not going to get much more in terms of an effective annual rate from that compounding. One thing about effective annual rates, which I think is important for you, if you look at your credit card statements, you often see, I'm used to seeing about 18% for an interest rate on credit cards. So if you get a loan from a credit card, you don't pay it off, you're going to pay about 18%. But I recently saw a credit card statement that said 30%. Actually, it was 29.99%. So somewhere there must be a state law that prevents it from going to 30%. So they specified 29.99%. Before we go any further, let's make sure we're clear on what this interest rate represents and what it's called in the industry, the credit card industry. It's called an annual percentage rate, and it's applied to consumer loans, which is what credit cards are. So an annual percentage rate is basically the I that we've been looking at, the interest rate for simple annual compounding. It doesn't reflect compounding within a year like we've just looked at with the effective annual rate. So what we need to do is we need to take that annual percentage rate and compute an effective annual rate to see what you're actually paying in terms of interest. It's very important that you have an understanding of this. The annual percentage rate is defined by law, and the reason for that is years ago, many financial institutions would have various ways of disclosing the interest rate. They tell you, well, this is the interest rate for a quarter, this is the interest rate for a month, and they wouldn't tell you the compounding effects, and it would be very, very confusing. It made comparison shopping for a low interest rate loan extremely difficult for consumers. So the law requires that they state an annual percentage rate, an APR, and the APR does not have compounding. It's the interest rate I that we've been using. And so when you read the fine print of a credit card contract, you're going to need to find out the compounding periods so you can compute this effective annual rate. So back to the problem at hand, where we have a 29.99% APR, annual percentage rate. Let's look at that, and And let's just assume it's 30%, round it so we don't have to deal with 29.999. Let's look at how that works for an effective annual rate. So the effective annual rate here will be 1 plus, call it 30%. And usually it's compounded monthly, although you have to read the fine print, get a microscope out, look at the fine print. But let's just assume it's monthly. And if we assume monthly, the effective annual rate is about 30.345 or 34.5%. So if you borrow money with a credit card and you don't pay it off, you're effectively paying almost 35% per year in an effective annual rate. And let's say, for example, well, what happens now if you don't pay off $1,000 and for some reason, you don't pay it off for 2 years and there's no other transactions occurring, you haven't paid anything off, and you go for 2 years, how much are you going to pay in the end to pay off the whole thing after 2 years? Well, you're going to take you're going to multiply this by, let's multiply 1.345 squared. And when you do that calculation, you'll get $1,809.25. In other words, you're going to have interest expense of $809.25. Whew, that's really high. Especially in today's world, interest rates are not that high. They've been kind of low for over a decade. They're starting to inch up now because of inflation possibly popping up. But, you won't find too many interest rates at nearly 35% unless you look at the credit card world. Now let's look what happens when we solve for n. Let's solve for n, the number of periods. Normally what we've been doing so far is we've been solving for a dollar amount. So let me give you a problem. Let's suppose we have a present value, it's 1,000. Future value is 0. The interest rate per year, I, is 7.93%. And payments are $250. And the question is, what is n? Okay. What is n? Now, we could solve this using this formula. So we have a present value of an annuity. And by the way, this is an annuity because you have payments here. And that equals the payments times this formula. So I'm using I, the formula in the textbook, which is the same as I/Y in your calculator. So we could say, look, this is 1,000. This is 250. And then this is 1 minus 1 over 0.0793 to the n power over 0.0793. Solve for n. Ooh, that's kind of a headache to solve for mathematically. It's one equation, one unknown, but you're going to have to do some somersaults. You divide both sides by 250. You'll get 4 here. Get rid of these brackets. Multiply things out. A lot of work. Bang this out on your calculator. That's the advantage of a financial calculator. Or, the other way to do it is you can just try to guess. Plug n's in until you get it. But let's not go there. If we plug this into our calculator and we hit compute n, out will pop 5. So over 5 periods, if we get $250 and interest rates are 7.93%, the present value of that investment will be worth $1,000. So that's how you solve for n. Now, we could also solve for an interest rate. So if we have a future value, and here's another, there'll be another example. So we have a future value. Let's just say it's $9,000. Let's say the payments are $800. Let's say the present value is 0. Let's say n is 7. And we want to compute I/Y. In other words, what is the interest rate that takes this $800 over 7 periods and brings it up to $9,000. So you would draw a timeline if you'd like here, and I'll just draw a number of dashes here. And basically you're going to come up with $9,000. You're going to pay, this thing will pay $800 for each of these years, including $800 here. And the question becomes, well, what is the interest rate that'll take this $800 to $9,000? Well, first off, $800 times 7 is going to be $5,600 if there's no interest rate. If the interest rate's 0, it's going to be $5,600. So you need to have a high interest rate to get $5,600 actually into $9,000 in these 7 years. So if you solve for this, it'll come out to be 15.53 on your calculator. There's an alternative method. Recall this formula. Future value of annuity equals a payment times 1 plus I to the n minus 1 all over I. And you could be trying to solve for this I, but this is a nightmare to solve mathematically because you got I up here, it's with an exponent, and then it's down here in the fraction. A real headache to solve. Your financial calculator solves it really quickly, and you come up with 15.53%. And by the way, you could quite easily, well, you could in a spreadsheet, for example, calculate this 9,000 really quickly with the 15.53%. So this is not a black box. You can do this. You would take this cash flow, compound it over one, count out the number of periods, compute it out, take this cash flow, compound it out, this cash flow, compound it out, and just continue. You'll come up with $9,000. And so you can check your work that way. So now there's one more problem that I want to cover that we often see in this course, and that is, how many periods will it take you to double your money? How many periods will it take you to double your money? Well, the way to look at this, and this is tricky, even if you have a financial calculator, you won't quite know how to handle this. But let me show you how to set it up. Let's just assume you invest $1, and it's going to be 1 plus I. We're going to assume annual compounding over n periods will get us $2. So notice I start off with $1, I end up with $2, so my money has doubled. And if I said how long will it take for me to triple my money, or you to triple your money? Well, this would be a 3. You start out with $1. So when you start out with $1, what's really cool about this is get rid of it. It doesn't do anything because you're multiplying it by 1. So multiplying anything by 1 doesn't do anything. Now the trick is you need an interest rate to solve this, obviously. And let's assume the interest rate's 10%. So 1.10 to the n power equals 2. Ooh, how the heck do I solve that? Because this is an exponent, and this is where people get stopped in their tracks pretty quickly. Well, here is the trick. And the trick involves getting your calculator out, and any calculator, doesn't need to be a financial calculator. See his little LN natural log button. That's the key. Because it turns out, if you take the natural log of both sides, this becomes n times the natural log, that's ln, of 1.10 equals the natural log, that's ln, of 2. And this becomes n times the natural log of 1.10. So type into your calculator 1.10 and then hit the ln button, and you'll get this, and this will be 0.0953. And then take the natural log of 2, put 2 in, hit the natural log, you'll get 0.69315, and then n, just divide both sides by 0.0953, and n will equal 7.27 years. So it will take you a little over 7 years at 10% to double your money. That's how you interpret it. There's a little bit to it with natural logs. If you're not familiar with natural logs, if you have y equals a times b to the c power, then what's cool about natural logs, it'll linearize this, because this would be non-linear. It'd be, curving this way if you had positive numbers. So what you do is you take the log of y equals the log of a, and that's natural log, plus c times the natural log of b. And this will work. So this side equals this side, and here this side equals this side. But notice you get the c down here as multiplication and not an exponent, and that's how it becomes easy to solve. Up here we had basically this formula. I said, look, we take $1 and take it to the n power, and it's 7.27 years equals 2. Okay, so now let's see if we take the natural log of both sides, we come up with the same answer. So we take the natural log of both sides, we're going to get, this will be 0.69315. We just saw that a minute ago, right here. And we'll take the log, let's take the log of 1. That's basically the log of a here, but the log of 1 is 0. So it doesn't do anything, so it's 0 plus 7.27 times the log of 1.10. And we know that that's this right here is 0.0953. So 7.27 times 0.093 is the 0.69315. So it works. Here I have a spreadsheet that works the problem that I covered earlier, where we calculated a 15.53% interest rate on an $800 annuity for 7 years. And there we have it. The future value of each of those cash flows sums up to just under $9,000. And I got a little bit of rounding because I rounded that 15.53% interest rate. That was rounded. If I would have brought that out a few more places, we'd be right at the $9,000 mark.